Hi, Bobcats. As we're finishing up chapter 14, I wanted to wrap back around and add a couple more topics. When we moved online in spring of 2020 and all of this got reworked for the new online format, I decided to focus on big picture stuff, and there were a couple of details that I let slide, but these details really are a big part of how all this kinetic stuff hangs together. And so now that we're back in in-person classes, I wanted to go ahead and add these back. Okay, then the first of these details is to examine a bit more closely how the overall reaction rate, the rate of disappearance of the reactants, and the rate of appearance of the products are all connected. And then also to take a much closer look at the connection between the overall reaction order and the units that are found on the rate constant. Very early in chapter 14, we looked at how we would write the rate expressions in terms of the different reactants and products. And so, for instance, for this particular reaction, we could write the rate of the reaction in terms of N2O5 or NO2 or O2. And experimentally, you're probably just going to monitor one of these chemicals. I would guess for this reaction, you'd monitor O2 because there are various sensors out there that are sensitive to O2. So based on the rate at which O2 appears, we want to be able to write what the rate of the reaction is. But if we were to monitor NO2 instead, the rate of appearance would be 4 times as much, because every time you get one O2, you're also getting 4 NO2s. Or if we were looking at how N2O5 was disappearing, for every one O2 that appeared, we would lose 2 N2O5s. So these numbers all get multiplied by these coefficients. And so we really want just a single uniform number for the rate of the reaction, no matter which chemical we're monitoring. So the process, the formalism that we use is that the rate is equal to, well, if it's a reactant, we're going to take minus 1 over the coefficient times the change in that reaction over the elapsed time. If it's a product, we're going to have a positive sign, but we'll still take 1 over the coefficient. And notice if the coefficient is 1, like in the case of O2, 1 over 1 is 1, and so we don't even write it. It's just the change in O2 over the change in time. Now, the type of problem I want you to be able to work is where they give you the rate of change of a particular chemical, and they ask you to find the rate of change of a different chemical, or the overall reaction rate. And so given one of these pieces, we should be able to use some very simple stoichiometry with the coefficients in moles in order to go from one expression to another. As a concrete example, we will look at the Haber process for the production of ammonia. This one's often used because each one of the chemicals has a different coefficient. In this particular case, it says the rate of appearance of ammonia is reported as 1.15 moles per liter per hour. And what is the reaction rate? Well, we're told the rate with respect to ammonia, and ammonia has a coefficient of 2 in the balanced equation. So to get the reaction rate, we will take 1 over the coefficient, and since ammonia is a product, we just keep that a positive number, and then times the rate of change of ammonia. So 1.15 moles per liter per hour. Remember that moles per liter is molarity, so this is often written as molarity per hour. And then if we're going to just go ahead and finish that on out, we would need to take the 1.15 and divide it by 2, and that's going to give us 0.575 moles per liter per hour for the overall reaction rate. On the next slide, we're going to use the same data, but see how we would express the rate of the disappearance of a reactant, for instance. Okay, so this is just a follow-on to the previous slide. We're given information about the rate of appearance of ammonia, but in part 2, we're asked what is the rate of disappearance of nitrogen. So nitrogen's a reactant. By throwing in words like appearance and disappearance, we're using the words to take into account the signs. Those of you who've had calculus and done all of these rate of change problems, I apologize for that. It's just the formalism in chemistry that we always show the rates as positive numbers. And so we end up using words like rate of disappearance to make sure that that does have a positive number. So anyway, here's what we have. We have 1.15 moles per liter per hour. And in particular, what we were given was data about ammonia. So that's actually moles of ammonia per liter per hour. And we're asked to express this instead in terms of nitrogen. Well, we're just going to use the coefficients from the balanced equation in terms of moles. We have, in our dimensional analysis problem here at the beginning, we have moles of ammonia. So in the bottom of my next step, I definitely need moles of ammonia to make it cancel out. And in the top, we're going to put moles of nitrogen. And we're just going to use the coefficients here. For every 2 moles of ammonia, there is 1 mole of nitrogen. So if we go ahead and run the math here, we once again have the 1.15 divided by 2, which is 0.0575. I'm sorry, I lost my pen. There it is. 0.575 moles of nitrogen per liter per hour. And we'll do pretty much the exact same thing in the last part. It's asking us to express this in terms of the disappearance of hydrogen. So we'll start with the 1.15 moles of ammonia per liter per hour. And we'll multiply this. Well, the bottom of the next step has to have moles of ammonia, and the top should have what we're looking for, so moles of hydrogen. When we look at the coefficients in the balanced equation, ammonia has a coefficient of 2 and hydrogen has a coefficient of 3. And so this is going to be 1.15 times 3 divided by 2, which is going to give us 1.725. Probably should just keep 3 sig figs, so 1.73 moles of hydrogen per liter per hour. So all we're doing is using the stoichiometric coefficients to convert from ammonia, which is what we were given, to the different chemicals, nitrogen and hydrogen. So if we were to have experimental equipment that allowed us to monitor nitrogen more reliably than we could monitor ammonia, we would be measuring 0.575 moles per liter per hour for nitrogen. So this is just different ways of expressing the rate, whether it's in terms of the overall reaction rate or the rate of appearance of a product or the rate of disappearance of a reactant.